So we are going to do capacitors and RC circuits. So first we will start with capacitors. So capacitors part is a little easier than RC circuits. So we will try to do this part very quickly and then move to this. So first what I'm going to do is I'm going to start with the capacitors. So just like in resistors, very similar to resistors, when we have combinations of capacitors, what we can do is we can write the equivalent capacitance. Equivalent means here these three capacitors are in series. What is the capacitor that we can write or draw instead of all the three? It is your equivalent capacitor. So we did very similar things to resistors, right? However, so let me write the equations that we got for resistors. For resistors when they were in series, what was the equation we got? Req was the addition of all, right? And when the resistors were in parallel, Req was the inverse, the addition of inverse stuff. So we add them and take the inverse again. So but in capacitors, it is exactly opposite of these two equations. So here we have the capacitors in series, right? So our equivalent capacitance is the opposite of this. So what is the opposite of this? It is 1 over C1, 1 over C2. You add them and take the inverse. So the equations are kind of jumbled in like between capacitors and resistors. So when they are in series, this is how you calculate the equivalent capacitance. Okay. Now what we are going to do is we are going to answer these 4 questions. So if we can answer these 4 questions, you will know everything that you have to know about capacitors in series. Okay, so let's start. As a start, I will explain what is happening in this. So when we have a battery like this, so this side is positive terminal and this side is the negative terminal of the battery, right? So since this is the positive terminal, what happens is this side of this plate is going to be positive. Because this battery, this side of the battery is only connected to this plate, right? This side of the battery is connected to this plate. So because of that, this plate is going to be charged positive. So let me call that charge positive Q. And in the same way, the negative terminal is connected to the this plate of the third capacitor. So what's going to happen is charges are going to move and this plate is going to be negatively charged and it is going to be same as this Q, but it is negative. Okay. So our battery will only give charges to this plate and this plate. So let's see how other plates are going to be charged. In a capacitor, so let me draw a new capacitor. So in a capacitor, what do we have in the middle? We have either nothing or an insulating material, right? A dielectric. So whatever inside is not conducting, right? Whatever inside is not conducting. So charges are not going to go from this plate to this plate through conduction. That can't happen, right? Charges cannot move through an inductor to this plate. Insulator to this plate. So what is going to happen is this plate is made up of metal. It's a conducting material. So since this plate is negative, positive charges are going to be attracted to this side. Through induction, we know when we bring a negative thing near a conductor, positive charges are going to be induced, right? So positive charges are going to be induced and it is going to be equal to plus Q. Okay, so in the same way, so now positive charges are on this plate. What's going to happen to this plate now? So these two plates are connected. If this side is positive, this side will be negative because the whole thing is neutral, right? This whole thing is neutral. If this is positive Q, this is negative Q. So if this is negative Q, this is going to be positive Q. Again, induction. So in the same way, if this is positive, this is negative. So the battery only gave charges to this side and this side, right? So from the battery, only it only provided charge enough to charge one capacitor. It only gave charge enough to charge one capacitor. So the battery gave just Q. Everything else, all the other capacitors in the middle and all the other plates were charged due to induction, right? So all the other ones charged due to induction. And the other important thing is all the plates, all the capacitors have the same charge, right? Can you see it? So all of them have the same charge. Okay. So now we know that. Can we answer the first problem here? First question here. What is charge on each capacitor? What can you say about the charge on each capacitor? It is the same, right? Same charge. Okay. So we are okay with the charge. I hope we are okay with the charge. Yes. Okay. So I'm going to erase some of this. No, I'll use a different color. Okay. So in the next part, I'm asking about the voltage across each capacitor. What can you say about the voltage? Anyone? You can tell me in the chat. What can you tell about the voltage? Is it the same or different? So what is the voltage across the first capacitor, second capacitor, and the third capacitor? Are they the same? So I'm getting the correct answer. Yes, they are not the same. Why? Because we know this battery, let me write VB. The voltage of the battery is divided among the three capacitors, right? From Kirchhoff's law, we know voltage of the battery is given by V1 plus V2 plus V3, right? So the voltages are different. They are different. How can we calculate the voltage of each? Using this equation. This is the general equation for a capacitor, right? In a charged capacitor, we know Q equals CV. So if we rearrange this, we get V equals Q over C. So for the first capacitor, V1 For the first capacitor, voltage will be Q over C1. So are we okay with this? Yes. So for the second capacitor, we have the same charge, right? We know when they are in series, they have the same charge. It will be Q over C2. For the third capacitor, it will be Q over C3. So even with these equations, we can see that the V's are different because C's are different, right? When the capacitance values are different, when your capacitors are different, your voltages will also be different. But when we add the three voltages, when we add them together, we should get the value of the total voltage, VB. So are we okay with the voltage part? So we are good. Okay. So the next part is, so we know how to find voltage. We know the charges are the same. But the problem is, how can we find the charge? So we need the charge. We need Q to find the voltages. But without knowing Q, we can't do anything. So how to find this Q? So to find it, let me use blue color. So to find Q, what we would do is we would use the equivalent circuit. So what we would do is we will use this circuit because this is very simplified version. This is a simplified version, right? So if we use this circuit to find the charge given by the battery, we know it will be same in all the capacitors because charge given out by the battery is the exact same thing as the charge in all the capacitors, right? All the capacitors have the same charge. So for this, what we would do is we will use Q equals CV, but we will use the equivalent capacitance for the C. And for the voltage, we know it is the voltage of the battery, right? Across the equivalent capacitor, we have the voltage of the battery, VB. So this is how you calculate the charge when your capacitors are in series. You find the equivalent capacitor, you find the equivalent capacitance, and then plug it into Q equals CV to find the answer. So are we okay with this? Okay. So the next part, how can we find the energy? So one way to do it is find the energy of individual capacitors, which will be time consuming, right? If there were 100 capacitors, you will have to do it 100 times. It's not easy, right? So what we would do is we will use the equivalent circuit. So equivalent circuit means this is same as this circuit. Okay. So if we use this circuit to find it, we can use any of the equations. I like to use this one. Half CEQ equivalent capacitance times the voltage across the equivalent capacitor, which is the voltage of the battery squared. So if you want, you can use any of the three, okay? You can use any of the three. So are you okay with these four things? Yes. And so can you remember the special thing about this equation? When in resistors, I said when we have this equation, the resultant we get or the answer we get is always smaller than the smallest. Remember? So higher the number of capacitors you have, smaller the equivalent capacitance. Okay, so this is just additional. So let's go to the first problem. So there are 3 problems. All the 3 are conceptual problems. Do it and tell me the answer as soon as you can. Okay. So all your answers are correct. D, D, B. So I'll first mark the answers. D, D, B. And go through them. When 2 or more capacitors are connected in series to a battery, the total voltage across the combination is the algebraic sum. So it is correct, right? VB was V1 plus V2 plus V3, right? So this is correct. Each capacitor carries the same amount of charge. So that is like the definition, right? So all the capacitors, when they're in series, have the same charge. Okay. In third one, the equivalent capacitance of the combination is less than the capacitance of any capacitor. That is correct, right? We know this equation. It's what I said at last, right? In the previous slide. So special characteristic of equations like this is the value you get is smaller than the smallest. More values you have, this value drops. So your answer is all of them are correct. Second question, as more and more capacitors are connected in series, so as we know, when we connect more and more capacitors, the equivalent capacitance drop, right? It always decreases. What they're saying is the equivalent capacitance increases. Wrong, right? It never happens. So the answer is never true. Always it drops. Even if you have equal capacitors, let's say you have 2 equal capacitors. Let's say 5 microfarad. Let's say 6 microfarads and 6 microfarads. So this will give you the equivalent capacitance of 3 microfarads. Okay. If you have 3, it will give you 2 microfarads. So even if you have the same value capacitors, when there are more and more, the equivalent value drops. Okay. If you have 6, let's say you have 6 capacitors of 6 microfarads, 1, 2, 3, 4, 5, 6. Then you will get 1 microfarad. So more and more capacitors you have, your capacitance, equivalent capacitance drop. Okay, so the third one, 3 identical capacitors are connected in series to a battery. If the total charge of Q flows from the battery, how much charge does each capacitor carry? We know, let's say we have around 5, we have 3 capacitors connected to this battery. We know the capacitor only give charges to these 2 plates, Q, Q. So that is what is meant by this. If Q goes out from the battery, how much charge does each capacitor carry? It's also same as Q, right? All the capacitors get the same charge. So your answer is Q. So this is important, this part. So battery gives out Q. if the battery gives out Q, all capacitors to have Q, right? Each of them have Q charge. Each of them is having Q. But when we go to the next section, when the capacitors are parallel, this will be different. So you can write this down for a series. Okay, for a series, battery and all capacitors have the same thing. So we can compare it with the parallel case when we go to that. Okay, so these were the conceptual ones. Now we have problems. So these two are the exact same problem, but I'm asking about two different things. Okay, so do this and tell me the answers. So we have 3 capacitors connected in series. And they are connected to a battery of 12 volts. This is 5 microfarads, this is 10 microfarads, this is 50 microfarads. So they are asking how much charge is stored in the 5 microfarad capacitor. We know whatever the charge given by the battery, if it is plus Q or minus Q, all the capacitors are going to have the same charge, right? So whether it is 5 microfarad capacitor or any of the other two, it's the same. So all the charges are the same. So how can we do this problem? If you remember the summary that we did on the first slide, what I said was for a problem like this, what we should do is we have to calculate the equivalent capacitance. So once we do that, we can use Q equals CV for this small circuit, for the reduced circuit, to find the charge. So that is what we are going to do. So my first step is finding the equivalent capacitance. So CEQ is given by 1 over 5 plus 1 over 10 plus 1 over 50 inverse 1. So I have got 3.125 microfarads. So we can see that this value is smaller than the smallest. It's smaller than 5, right? Okay. So now we have the equivalent capacitance. We just have to plug it into this equation to get Q. So let's find Q. QV CEQ 3.125 micro is 10 to the negative 6. Then my VB is 12. So this is microfarad. I converted it into farads, and this is 12 volts. So when we do this, we get 3.75 10 to the negative 5 coulombs. They have given the answer in microcoulombs, right? So what I'm going to do is I'm going to convert it into 10 to the negative 6. 10 to the negative 6 is micro. So your answer is 37.5 microcoulombs, which is C. So all of you gave me the correct answer. So you all know what to do, right? Like when we have a series circuit, you would calculate the equivalent capacitance to get the charge. And the charge you get here is same as the charge in any of the capacitors. Okay. So in the next part, what are they asking? They are asking us to calculate the voltage or the potential difference across the 10 microfarad capacitor. So how to do it? They're asking us to calculate the voltage across this, right? So if you remember, when we have to calculate the voltage across a capacitor, what we should do is we need to use Q equals CV. So from that equation, I get V is Q over C. And since we are finding the voltage across this, so I'm finding the voltage across the 10 microfarad capacitor, right? So I should substitute the Q in this divided by the capacitance of this capacitor. So the Q in this is same as this Q value, which was 37.5 microcoulombs. When I convert it to coulombs, it is 10 to the negative 6. So this is the charge in this capacitor. And the capacitance is 10 microfarads, right? 10 to the negative 6 microfarads. So when we divide it, we get 3.75 volts. So your answer is C. So all of you got that answer. Easy, right? Okay. So this is fine. Now let's move to the next one. So that's it. Okay. So now we are moving to parallel circuits. So I have the same questions as the previous case. I have changed the order so that this order makes more sense. And let's see what is happening. So here our capacitors are connected in parallel to each other, right? They are parallel. So when they are parallel, the equivalent capacitance is given by just the addition of each of them. So you just add them. See, this is exactly opposite to resistors, right? In series resistors only we did this, but in parallel capacitors we do the same thing. So we add the three capacitors to get the equivalent capacitance. Okay, now we know this equation. Let's go to these parts. Let's see what is happening in this circuit. So this is my capacitor, this is my battery. Let's say the voltage is VB. So if the voltage across this battery is VB, the voltage across all the three capacitors is also VB, right? The voltage across this is VB. Voltage across this one is also VB. Voltage across C3 is also VB. So that is parallel connection, right? When things are connected parallel, they have the same voltage. So voltage across each capacitor is the same. And if it's having this arrangement, if it's directly connected to a battery like this, it is same as VB. What can you tell about the charge? What can you tell about the charge on each of them? If you like remember from the lecture, should they be the same or are they different? Different. So they are different. So let's see what is happening. Let's calculate the values. So what I'm going to do is I'm going to use the capacity equation. So the charge in the first capacitor is given by the capacitance times the voltage across that capacitor. So voltage across it is VB. So in the same way, I can do this for the other two capacitors. Charge in the second one is capacitance of that times the voltage across it. Charge in the third one is its capacitance times charge across it. So here you can see that the charges are different, right? Although the voltage is the same, although VB is the same, charge on each of them will depend on the value of the capacitor, right? Okay, so they are different. What can you tell about this? So what is the charge given out of the battery? And what is the charge of each capacitor? So each capacitor we know, right? Each capacitor we know they are different and each of them are having these values. What about the charge given out of the battery? So all these charges were given out of the battery, right? These capacitors got this charge from this battery. So the total charge given out of the battery is, so Q total is Q1 plus Q2 plus Q3. So it is different from the series, right? In the series, battery also gave Q value, and each of the capacitors are also having the same value. But here, battery charged all the capacitors, not only the two plates, not only the last two plates like in the series one. So here battery charge given out of the battery is the addition of all the charges, and charge in each capacitor we know how to calculate. Okay, so how to find Q we know. We know how to find Q of individual capacitors and also Q of the battery. So we are good with this. So my last problem, how to find the energy. How to find the energy stored in this. So similar to the previous one way is you find energy, total energy, if you find energy of each capacitor and add them. But we don't like that method because it's time consuming, right? We don't want to do this. So the other way is you use the equivalent circuit. Equivalent means you find the energy of this circuit. So if I do this energy of the whole thing, all the capacitors is half times, I'm going to use this equation, the equivalent capacitance times V squared. So this part is very similar to the series case. You just use this equation. So are we okay with this? So these are the, if you know these answers to these four parts, in both series and parallel, you can do any question in series parallel capacitors. Okay, so let me move to the problems. Okay, so here I have two problems. Do it and tell me the answer. The first one, as more and more capacitors are connected in parallel, We know the equivalent capacitance is given by the addition, right? When you have more terms, this value is going to increase, right? So it is always going to increase. Always true. In the next one, so you have two parallel capacitors and one in series, right? So if I draw it, so this is 10 microfarads, this is 20, and I have a 30 microfarad. So they're asking us to find the equivalent capacitance. So I'll start with these two. They are parallel, right? So how to find the equivalent of parallel ones? You just add them. Okay. There is a difference between resistors and this type. So you just add 10 plus 20 and you get 30. Okay. So your next step is this. So instead of 10 and 20, now we have 30 microfarads. And again, we have 30 microfarads here. Now these two are in series. So when they are in series, how do we add them? By taking the inverse. 1 over 30 plus 1 over 30, inverse 1. So when we do that, we get 15 microfarad. So I've seen in exams, a lot of people get confused. They just forget the equation and they do what you do to resistors. Okay. So the resistors and capacitors are exactly opposite when we do equivalent resistors. So your answer is B. So are we okay with this? Yes. So I will move. So here we have an energy problem. Do it and tell me the answer. So here the capacitors are connected in parallel. So your EQ is just the addition of the 3, right? So it is 6 microfarads. How much energy is stored in the combination? So we know how to find the energy. Half CEQ times the voltage across CEQ. So half times capacitance is 6 microfarads. So we have to convert it to farads. And the voltage is 24 and it should be squared. So when we do this, I have got 1.728 10 to the negative 3 joules. So the answers are in millijoules, and also the problem has two sig figs, right? So 1.7 millijoules. So your answer is A. Now let's start the hard one. This is not really hard, but it can be very confusing. So we will try to go step by step because this is very important. So here I have a circuit which has a resistor and a capacitor. So circuits which has resistors and capacitors are called RC circuits. So RC circuits is nothing special. If it has a resistor and a capacitor both, or a bunch of resistors and bunch of capacitors together, they are called RC circuits. So this is our RC circuit, right? We have a resistor and a capacitor. So let's assume that this capacitor is not charged. Okay, this is not charged. So it is a blank capacitor. Nothing is there, no charge. So and I have connected it to this circuit and I haven't closed the switch. That means still the circuit is open. No current or nothing flows through it yet. Okay. So are we okay up to there? That's fine. There's nothing still, but let's start it now. So let's assume a scenario where I close this circuit. Closing means now the circuit is connected. Okay, now the wires are connected. A closed circuit. So I'm going to look at t equals 0. T equals 0 means the moment I close this switch. So before going into that, let's look at the voltages in the circuit. Okay. So we have R and C, resistor and a capacitor connected to this battery. Since this is a closed circuit now, since I have closed the switch, the voltage given by the battery is equal to the voltage across the resistor times the voltage across the capacitor, right? From Kirchhoff law, we know the total voltage VB is voltage across the resistor plus the capacitor. So are we okay with that equation? Yes. So this is easy, right? Okay. So here I have written that equation. So the next step is, how can you find the voltage across the resistor? From Ohm's law, right? V equals IR. You all know that already. So how to find the voltage across a resistor? You multiply the current through it by the resistance, right? So our VR is equal to I times R. How to find the voltage across a capacitor? From this equation, right? Q equals CV. This is the equation of a capacitor, right? So voltage across the capacitor is given by charge of the capacitor divided by the capacitance. So are we okay with these two things? We know how these come, right? You all are very familiar with these two. So in this equation, what I have done is I have replaced VR with IR and voltage across capacitor by Q over C. So are we okay with this equation as well? So if we know this equation, these two equations, it's easy to do any problem. So are we okay with this? Okay. So I'm going to erase all the ink in this slide. Okay. So with this, so we will need these two when we are going to look at t equals 0 and this part. At t equals 0. T equals 0 means the moment I close the circuit, right? The moment I close the circuit, is my capacitor charged? No, right? I haven't even started charging the capacitor. We know we connected a capacitor which is not charged. So the moment I close the switch, still it is not charged. So at t equals 0, the charge in my capacitor is 0, right? So are we okay with this? That the charge in the capacitor is 0? Yes. So that is the starting point. If you can figure this part out, all the things become very easy. Okay. So my next question is, at t equals 0, what is the voltage across the capacitor? So we know voltage across the capacitor is given by this, right? This equation. So voltage across the capacitor is given by Q divided by C. So look at this equation and tell me what should be the voltage across the capacitor? What should it be? 0, right? So it is also 0. Why? There is no charge in the capacitor. So if you didn't know this, it's hard to figure this out, right? It can be very confusing to just think of the voltage across the capacitor. So always go in this order. Okay. Since the capacitor is not charged, charge is 0. Voltage across a capacitor is given by this equation. So because of that, voltage across the capacitor is also 0. So we are okay with these two. So the next question is, what is the voltage across your resistor? So if I rewrite the equation, we know voltage of the battery is given by voltage of the resistor plus voltage of the capacitor, right? So we figured out at t equals 0, voltage across the capacitor is 0. So if that is the case, what is the voltage across the resistor? It is completely VB, right? The whole voltage of the battery is now across your resistor. So it is equal to VB. So this is the maximum voltage that we can have, right? Because voltage is given by the battery and the resistor is taking all the voltage now. So this is the maximum voltage the resistor can have, right? Also we know this is equal to IR. Okay, so you are okay with VR. So at t equals 0, the whole voltage is with the resistor. There's no voltage for the capacitor. So last part, what is the current through the circuit? At this point, what is the current through the circuit? So current is connected to the resistor, right? So we can figure out current from this part. We know for the resistor voltage was VB and it was equal to I times R. So from this we can get the current. Current is VB divided by the resistance. So this is the current through your circuit at t equals 0. At the moment you close the switch, this is the current which will go through the circuit. And this will also be the maximum current, right? Because voltage is maximum here. This is the maximum voltage. Therefore, at t equals 0, the current through the circuit will be maximum. This voltage is maximum here. Okay. So are we okay with this, and this? Yes. So this is very important. And most of the conceptual problems will ask you about this. So conceptual problems on this will be at t equals 0, what is the current through the circuit? At t equals 0, what is the voltage across the resistor? So they can just ask you things, but you have to know to go in this order. So go in this order, write it down inside of in the side of a paper. Then you can just look at this and answer. So you are okay with this. Now let's go to the other scenario. So this is one very important at t equals 0. Now this is at infinity. So when t is infinity means now your capacitor is fully charged. But that is what they mean by infinity or long enough. When you wait long enough, your capacitor is charged. Okay? What is meant by infinity or long enough is your capacitor is fully charged. Okay. So this is something that you have to know. Let's start from current in this. Okay. So when your capacitor is fully charged, okay, fully charged means now this plate will have plus Q and this plate will have minus Q, right? Fully charged. Current will no longer pass through the circuit. Okay? That is like a fact that you have to know. When it is fully charged, there is no way that, no reason for the current to flow, right? Because there is a gap in the middle. And since these two plates are having the full capacity of charges, even charges will not move from this plate to this side or this side. So if you wait long enough till your capacitor is charged, the current through the circuit will be 0. Okay, so that is the starting point of this. When you start with this, you can keep on deriving the others. So are you okay with this? This is something you have to know. Remember, okay? When your capacitor is completely charged, no current will flow through the circuit. Okay, now let's go to this part. If current doesn't flow through the circuit, what is the voltage across your resistor? So voltage across the resistor is given by this equation, right? This expression. So it should be 0, right? No current, no voltage. So we get the voltage across the resistor through this equation. So the voltage across your resistor, is 0. This is 0. So we are okay with this. Why do I keep cutting things today? Okay. Now can you tell me this one? What is the voltage through your capacitor? So I'm getting the answer very good. So it is VB. So we can use this equation, right? You know VB is equal to VR plus VC. So we know the voltage across the resistor is 0. Because of that, the whole voltage VB is now with the capacitor. Voltage across your capacitor is now VB and it is maximum. So voltage of the capacitor becomes maximum when we wait for a long time, right? So if I kind of draw the diagram, at t equals 0, voltage across the capacitor was 0, right? At t equals infinity, voltage across the capacitor becomes VB. So it is increasing with time, right? So in the next slide, we will learn about this curve. So it is increasing like this. So we will learn about this equation later. So we know this, but can you tell about the charge in the capacitor? Very good. So we know Q equals CV. So now the capacitor has a voltage of VB across it. So your charge QC is C times VB. This is the maximum charge, right? It makes sense, right? At the moment you connect the capacitor, it won't be charged. So after some time, it will be charged. So it also kind of follows the same similar trend. Charge of the capacitor, also follows a trend like this. At t equals 0, nothing. When you wait long enough, it comes to the maximum. So are we okay with this? Yeah. Okay. So you are okay with these shapes, right? You understand that at t equals 0, this is 0 and this is increasing. What about the resistor? No, let's look at the current. So at t equals 0, so current through the circuit, it was maximum, right? See, it was maximum at t equals 0. And it was 0 after some time. So it starts from 0 and go to 0. Start with the maximum and go to keep on reducing. So if you know these two things, A and B, what is the condition when time is 0 and what is the condition at infinity or till you wait till it's fully charged. If you know this, you can figure out the shape of the curve, right? Okay, so here I have a summary of what we did in the previous slide. So this is a summary. So we know what is happening at t equals 0 and what is happening at t equals infinity, or once your capacitor is completely charged. So now your capacitor is completely charged. So that is what we usually call infinity. We give enough time till the capacitor is fully charged. Okay. So we can see that the charge in the capacitor has increased. Voltage across the capacitor has increased. Current to the circuit has decreased. And the resistance, the voltage across the resistor has decreased. So like I said in the previous slide, we see two types of behaviors, increasing behaviors and decreasing behaviors. So the good part is that all of these behave into only in two ways. So what I mean by two ways is anything which increases, anything which has an increasing trend, for example, let's consider Q for now. So Q has an increasing trend. We'll have this equation. So the Q right now, Q at time t is equal to the maximum Q value we can have times, so this is a bracket, 1 minus e to the power negative time divided by RC. So this is the general equation for the increasing trend. You have so this is the value at time t. And this is the maximum value your Q can have. And then you have 1 minus E t to the t divided by RC. So if I rewrite this equation with the maximum Q value, we know the maximum Q value the capacitor can have is C times VB. So if I replace it, the maximum Q value with C times VB, this is my equation. And in the same way, we have an increase in trend for the voltage across the capacitor. So if I follow the same format, the voltage or the potential difference So this is the potential difference at time t. It is equal to the maximum voltage it can have, Vmax, times 1 minus E t divided by RC. So if I rewrite this again, what is the maximum voltage it can have? VB, right? So your voltage at any time t can be found using this equation. 1 minus E t over RC. So can you see that? So these are the two quantities which shows an increase in trend. So they both have a very similar equation. They both follow the same format. The value at time t is equal to the maximum value times this part. So here also the voltage at time t is equal to the maximum voltage it can have times this factor. And if I draw the circuit, if I draw the graph, this is how it will vary. So it starts from 0 and it will reach the maximum. So this is the maximum value. Maximum value means this part. So for Q, it will reach this value. So if this is the Q graph, your maximum will be CVB. It will reach maximum at infinity. So in the same way, your voltage will also have a similar graph, but this graph will reach the maximum of VB at infinity. So this is the general format of your increasing trend. Easy, right? Okay. So we know what to do with increasing trends. The next part is, what about this? What about a decreasing trend? We can see the current through the circuit started from the maximum and then decreased. So when we have a decreasing trend, so I will use a different color. Okay, when we have a decreasing trend, your equation will be, so I'll start with current. So your current equation, so this is your I at time t. Time t means any time that you like. So if I want you to find the current at 2 seconds, what you would do is you will plug 2 to the place where we have t in the equation. So the equation is very similar to the previous one, but a little different. So it also starts with the maximum value the current can have. But now you don't have that 1 minus part. Instead, you directly have the exponential factor E minus T divided by RC. So if I rewrite this equation by substituting the maximum. So this is the maximum value the current can have. So your equation will be current at time t is equal to VB divided by R E negative T divided by RC. So in the same way, let's write the equation for VR. So this is also a decreasing trend. So voltage of R, voltage across the resistor at any time t, is equal to maximum value this voltage can have. So this is the maximum value it can have, right? So it is VB. Since it's a decreasing trend, this will be your equation, T divided by RC. So can you see that these are very easy? They follow the same trend. So if you know whether it's a decreasing trend or an increasing trend, you can easily write the equations. So these equations will look like this. It starts with the maximum. It starts with a maximum and then reaches 0 at infinity. See, at infinity, it will reach 0. So this is your decreasing trend equation. This is your increasing trend equations. So example, current equation and the voltage across the resistor. Here increasing trend R, Q, charge of your capacitor and the voltage or the potential difference across the capacitor. So are we good with this? Okay, now let's move to the problems. So here, the first one, a resistor and a capacitor are connected in series to an ideal battery of constant terminal voltage. At the moment contact is made with the battery, so they are talking about the RC circuit because we have a resistor and a capacitor in series to a battery. So let us draw it. So we have our battery, we have a resistor, and we have the capacitor. So the moment it is connected to a battery, that means they are talking about T equals 0, right? So they're asking what is the voltage across the capacitor. You know, at the moment it is connected, Q is equal to 0. Therefore, voltage across the capacitor is 0. Why? Q equals CV. And your voltage across the capacitor, this V is given by Q over C. So since there's no charge in the capacitor at time 0, your voltage across the capacitor is also 0. So your answer is 0. Okay. So in the next part, a resistor, so we have the same circuit, resistor and a capacitor are connected in series. Now they are asking us to find the voltage across the resistor. So here I haven't, in the summary part, I haven't written it down. Can you tell me what it would be? What is the voltage across the resistor at time 0? So we know voltage of the battery is divided among the resistor and the capacitor. Why? They are in series, right? This is the resistor and this is the capacitor. Voltage of the battery is equal to VR plus VC. But we saw that VC at time 0 is equal to 0. Therefore, at time 0, your VR or the voltage across the resistor is equal to VB. The voltage of the battery is completely across the resistor. So it is equal to VB. In other words, equal to battery's terminal voltage. So the third problem. A resistor and a capacitor are connected in series to an ideal battery at constant terminal voltage. So very similar to the previous part. Now they are talking about a steady state. Steady state means once your capacitor is completely charged. Okay. So once this reaches steady state, no longer charges are moving, it has come to an equilibrium. The voltage across the resistor is, so now they are talking about T gone to infinity, voltage across the resistor. What should it be? The voltage across the capacitor at time infinity is batteries or the terminal voltage, right? So from this one we can deduce it. VB is equal to VR plus VC. At time infinity, this is equal to VB. Therefore, your VR, voltage across the resistor, is 0. So you can also check our previous summary, how we derived this. So VR is 0. So easy, right? So now we have a problem. So there is a 20 microfarad capacitor and it is charged. So it is being charged through this resistor. So we have charged means there is a battery. Okay, there is a battery in the circuit. That is why they tell that it is being charged. So we have this battery which we don't know anything about, but we know the value of the resistor, which is 50 kilo ohms, and also we know the capacitance, 20 microfarads. They're asking how long does it take for the capacitor to reach 90% of full charge. 90% of full charge. Okay. So you can use both the equations, this and this one. If you remember the charge across the capacitor, C times VB. So you can use any of these equations. So fully charged means what? Fully charged means you have reached the maximum either voltage or the charge, right? So we can use both the equations. So I'll use this for now. But even if you use this, you will get the same answer. So this is my equation. So instead of CVB, I'll just write Q max for now. The maximum charge it can have, 1 minus E TORC. Okay. What are they asking? They are asking how long does it take? That means they're asking us to find time so that the capacitor will reach 90% of the full charge. That means your Q value should be 90% of Q max, right? So how to write 90%? 90%. How do you take a percentage? 90 divided by 100, right? So you need to reach 90 over 100 of your Q max. So I'm going to substitute these values. So I'm going to substitute this for Q. So if I simplify this, I'll get 0.9 Q max. So I want to reach this value, 90% of the full charge. And everything else in the equation is the same, and we will be solving for T. So I'm not going to substitute for R and C right now. We will substitute it at the end. So we can see that Q max is common to both the sides. So it will get cancelled and we are left with 0.9 1 minus E negative T over RC. So we need to solve for T. So what I'm going to do is I'm going to take this E term to the other side of the equation and bring 0.9 to this side. So 1 minus 0.9 is equal to, oops, it's okay, okay. E T over RC, so I'll rewrite it. So I will get E T minus RC, and on the other side I have 1 minus 0.9. So this reduces to E minus T over RC equal to 0.1. So this part is new to you. You might know it, but sometimes you might not know it. So how to solve this stuff? So to solve your E value, what you would do is, if you look carefully in your calculator, there will be something called ln. It is called the natural log. So when we take, so I'll write it here. So when we take the natural log of natural log of an exponential, for example, let's say e to the power x. When we take the natural log of an exponential, we get x. So we write whatever in the exponent, we get the whatever in the exponent as the answer. So if we have e to the power negative t over rc in the exponent, what we will be getting? We will get whatever here, right? So we will get negative t over rc as the answer. But this is an equation. Whatever we do to one side should be done to the other side. So we have to take the natural log of both sides. So we know how to simplify this part. We know when we take the natural log of an exponential, we get the answer as negative t divided by rc. But in this part, we don't know the value. We have to plug this in the calculator and get the answer. So if I do that, I get negative 2.3. So this is what I got. So since I don't have much room, I will do the rest in this side. So negative get cancelled. So we are left with t over rc equal to 2.3. So your t will be 2.3 times r times c. So what is your r? R was 50 kilo ohms. But we have to substitute in standard units. 50 kilo is 10 to the power 3. And what is your C? C is 20 microfarads. So 20, we have to convert micro. 10 to the negative 6. So once you solve this, once you simplify this, but the answer you get will be in seconds. So I have got 2.302 seconds. So it takes 2.3 seconds for your capacitor to charge 90%. So your answer is 2.3D. So is this clear? So this part is new to you. Some of you might know this, but you might need this to do problems. So I want you to learn this and practice this. Okay. So we are done with charging a capacitor, which is the hard part. Now we will go to discharging a capacitor. So discharging is easy. Why? We know at time 0. So discharging means what? Discharging means you have a fully charged capacitor. Now you have a fully charged capacitor. What you will be doing is you will remove it from the circuit. So in the previous circuit, we had a battery, right? So as long as this is connected to a battery, this will not get discharged. So what we are going to do is we are going to remove the battery. Okay, we are going to remove the battery and just connect your capacitor through a resistor. So what will happen? Now the charges stored in the capacitor will start to power your circuit. It will start moving and the charges will start dissipating. So your capacitor will be discharging. It will start discharging. So at t equals 0, what can you tell about at t equals 0? At t equals 0, it is fully charged, right? At the moment you remove from the battery. So at t equals 0, you have a completely charged capacitor, and we just completed the circuit. Your capacitor is still fully charged. So we know for a fully charged capacitor, so it is a fully charged capacitor. We know for a fully charged capacitor, the charge Q is the maximum. What is the maximum Q? It is C times VB, right? So it is VB. VB means the voltage of the previous battery, or the maximum voltage. So it is C times VB. VB is the terminal voltage of the battery you used to charge the capacitor. So it is same as what we did before. So Q will be maximum at t equals 0. And also we know voltage across the capacitor is equal to the terminal voltage of the battery. So from this equation you can get it. So that is our conditions at t equals 0 for the capacitor. What can you tell about the resistor? What is the voltage across the resistor? So here we don't have a battery in this circuit, right? We don't have a battery in the circuit. So whatever the voltage across the capacitor is the voltage across the resistor. So it is also VB. So this is different from the charging case. So what can you tell about the current? Current is given by V equals IR, right, for the resistor. So since the voltage across the resistor is also VB, it is same as the voltage across the capacitor. Therefore, there will be current. So your current will be VB over the resistance. So this discharging of a capacitor is very easy. Why? Every parameter is maximum at t equals 0. And with time, it will start dropping. So not only VC and Q, VR and current will also follow a decreasing trend. So we know the equation for a decreasing trend. So the equation for a decreasing trend is the maximum value it can have E T over RC. In the same way, for the current, it is the maximum value it can have E T over RC. Okay. So this is easy. For a discharging capacitor, all your equations have decreasing trend. Okay, now let's go to the problems under this. So we have a capacitor which is 2 microfarads and it is completely charged to 12 volts. So we know what this is, right? It is the voltage across the capacitor. At t equals 0, your VC is 12 volts. Then discharge through a 410 to the power 6 resistor. They're asking how long will it take for the voltage across the capacitor to drop to 3 volts. So we can use this equation, right? Voltage across the capacitor at some time, at time t, is equal to the maximum voltage E T over RC. So let's substitute the values. VC. So they want us to find the time when your voltage reaches 3. So VC is 3. V naught is 12. It's a maximum. E T over RC. So let's substitute for RC at the end. So when I simplify this, I get 0.25. How? 3 divided by 12 is 0.25. E T over RC. So you all know how to simplify this. So whenever you have an exponent, what would you do? You will take the ln, right? So you should take, since this is an equation, you have to take ln or the natural log of both the sides. So when I do that, so for ln 0.25, I get negative 1.3862. And for this, we know this is the factor, negative T over RC. So I'll do the rest here. So your T over RC, because negative is there in both the sides and it will get cancelled, is equal to 1.3862. So your T is equal to 1.3862 times R times C. Now let's substitute. Your R is 4 10 to the power 6 given in the problem, and C is 2 microfarads. We have to convert microfarads to farads. So when you solve this, you get 11.0893, sorry, 11.96 seconds. 11 seconds. So your answer is B.